Imagine walking into your office, opening a single filing cabinet, and suddenly you are buried alive in thousands of unlabeled, scattered documents. This mess is what computer scientists call raw data. It is a mountain of disconnected names, numbers, and test scores that don't actually tell you anything useful on their own. That is exactly where a computer steps in. A computer is built with one specific, vital purpose: to take that chaotic pile of raw data and transform it into organized, meaningful information. To pull off that transformation, the system relies on two essential components working together: hardware and software. Hardware is the physical machinery, the monitor you're looking at, the keyboard you type on, the things you can actually touch. Software is the invisible set of instructions telling that machinery exactly what to do. Mastering data entry means understanding how to orchestrate those physical tools and digital commands in tandem. It's the only way to rescue ourselves from the avalanche of raw data. The first step in this digital pipeline is getting our physical data into the machine. We do this using specific input devices. Take a look at this classic computer mouse. Inside the casing, there's a heavy, rubber-coated tracking ball. As you drag the mouse across your desk, that ball rolls, translating your physical hand movements directly into digital signals on the screen. But you don't always need a mouse to move a cursor. A light pen uses a light-sensitive detector to let operators point, select, and even draw directly onto the monitor surface. There is a catch, though. The computer cannot understand human language. The inputs we provide in high-level, English-like syntax have to be translated downward. That low-level format is machine language. It's a continuous stream of binary ones and zeros, and the only thing the computer's central processing unit can directly read and execute. So, these input devices and built-in translators act as a vital bridge, converting our human intent into actionable mathematical logic. Once that binary data reaches the processor, the invisible brain of the operation, the software takes over to decide what happens next. First, you have system software, like your operating system. Think of this as the backstage manager. It quietly coordinates your hard drives, allocates memory, and organizes folders without you having to ask. Then you have application software. These are the specialist workers hired to perform specific user-facing tasks. If you need to type up a document, you launch a word processor. If you need to analyze a massive column of financial data, you open a spreadsheet application, like Excel, which gives you specialized formulas to sort the numbers. Or if you need to share your findings with an audience, you use presentation software. It handles the visual layout, allowing you to easily drop in geometric shapes and format bullet points to make the data digestible. This hierarchy of management and specialization is the pulse of the system. Without it, the physical hardware remains inert, capable of processing even the simplest command. Eventually, the software finishes processing the data, and that information has to be returned to the real world. This is where output devices take over. The most common way to retrieve information is visually. For decades, this meant staring into a bulky cathode ray tube monitor before the industry shifted to the thinner, flat-panel LCD screens we use today. If you need a physical copy, standard printers get the job done. In heavy data processing environments, you might even see a line printer, a loud, high-speed machine designed to rapidly churn out continuous rolls of text. But standard printers struggle with massive graphics. For large-scale architectural blueprints or mechanical plans, operators rely on a plotter. Instead of spraying thousands of tiny pixels across a page, a plotter uses a robotic arm holding an array of colored pens. This allows it to draw smooth, continuous vector lines with extreme mechanical precision. Whether it's on a screen, a sheet of paper, or a massive blueprint, these output devices represent the end of the pipeline, placing the processed, meaningful information back into our hands. Understanding this entire pipeline from input to output is exactly what the NIOS data entry operations exams test for. This is a recent NIOS question paper. The examiners aren't just looking for vocabulary. They want to see if you can identify specific hardware components and their practical use cases. Memorizing a list of keyboard shortcuts won't be enough to pass. You have to understand the mechanics behind the interface, like knowing that a light pen is an input device, or how a laser printer's speed is actually measured. True competency means looking at a real-world problem and knowing exactly which application software and which output device you need to solve it efficiently. It means taking that initial, overwhelming storm of raw numbers and structuring them into a clean, finished product. A true data entry operator commands the full harmony of hardware and software, refining raw chaos into perfect structured meaning.